All right, 11.6, we have directional derivatives and the gradient vector. So I start with directional derivatives. So consider this. What if we want the rate of change of a function z equals f of xy, okay, so some sort of like surface type thing here, in a direction other than x or y. Okay, so we've already learned that with our partial derivatives, we can find the rate of change in the direction of x and the rate of change in the direction of y. But now what if we want somewhere in between, or even like we want to figure out the maximum rate of change of a function? Okay, we want to find, like I always think of the hill example. If we were to release a ball on a hill, which way would it go? So now we're going to learn how to do that. So we have some notation here. That is the directional derivative of f of xy equals the partial in x times a plus the partial in y times b, where u is the unit vector in the direction we want, and u equals AB. Okay, and remember too that we can do that with trig. Since it's a unit vector, A would be the cosine of theta, and B would be the sine theta. I should say equals. Okay, again, that's called your directional derivative. Okay, so a nice little example here for you. I'll leave the formula there. Find the directional. It could be interesting to compare my handwriting at the beginning of these versus the end. So maybe how quickly I'm talking and how frantic I'm getting. It always seems as soon as I make a mistake, I get thrown off. Okay, so find the directional derivative of this function in the direction of theta equals pi over 6 at the point 1, 1. Okay, so first of all, we need to get our unit vector in that direction that we want. Okay, so get a different color here. I'm still mad at myself for messing up the proof in the 11.5 video at the end. And then you mess it up that late and you can't restart it. So, anyways. All right, so we've got, you're like, just shut up and get to the lesson. Theta equals pi over 6. Okay, and again, if that is a unit vector, then we just have cosine of pi over 6 over here, which is square root of 3 over 2. And then we have the sine of pi over 6 over here, which is 1/2. So u would be square root of 3 over 2, 1/2. Okay. And if you go back up to here, what this is doing, it's kind of taking like All right. What is our derivative in the x direction going in the x direction, and our derivative in the y direction going in the y direction? And it's going to give us a vector. Okay, so we've got an x component and a y component. It's going to give us kind of like that resulting vector between them. Let's see, your partial in x of that is going to be 3x squared y to the fourth plus 4x cubed y cubed. And your partial in the y will be 4x cubed y cubed plus 3x to the fourth y squared. Okay, so before we get too far, they give us a point to use. So let's go ahead and get that in there. So we'd have 7, right? Just plugging it in, you get 3 plus 4, and same for y. Would also be 7. Okay, so our directional derivative then is just going to be 7 times the square root of 3 over 2. Well, you know what? I kept saying that it was a vector. It's not a vector. It's the actual derivative. We're going to get to the vector part. Okay. Plus 7 times 1/2. So we'll have 7 halves square root of 3 plus 1. Okay. So that is the actual like derivative in that direction. Okay. So if we were to draw a line, you know, your tangent line in the direction of pi over 6, this would kind of be like the slope of the tangent line. All right. But definitely what I was kind of getting ahead of myself there is we actually want that vector too. So we got to add to it the vector piece. So what we really want, like the directional derivative is great, but what we really want and what's really going to be more useful is our gradient vector. Okay. So let me just get here. Yeah, sorry, I'm just looking. Then they switch up the notation on me here a little bit. Okay, so if we take our directional derivative, another way we can write it is like this. Okay, you think about that dot product. If you do that dot product, you get this equation up here. Okay, so it's another way of writing it with vectors, okay, which would be same thing. Okay, so what we care about is this vector right here. This is called the gradient of f. It's a super important vector. And it's written, the symbol means gradient. It's kind of upside down triangle. Okay, and we know that that can also, we have a lot of different notations for our partial derivatives, and we have a lot of different notations for our vectors. So we could even use our partial notation like this, and we could do our linear combination form for our vectors. Okay, so then the directional derivative is the dot product of the gradient and the unit vector, just like that. Okay, so let's do a little example here. We'll kind of talk about what it means too again. So for example, let's say f of xy is y squared over x. And again, just like I've always encouraged you guys, as we're doing these, go on a 3D plotter and plot that surface and take a look at what it looks like. Okay. First step, we are going to find the gradient of f at the point 1, 2. Okay, and we're going to find the rate of change of f at 1, 2 in the direction of two I plus square root of 5j. Okay, so working through this. Okay, so first of all, the gradient is your partial derivatives. Okay, so our partial derivative with respect to x, let's see, so it would be negative y squared over x squared. And your partial with respect to y would be 2yx. Okay. Now, that vector, okay, is your gradient vector. Okay, the gradient vector points in the direction of maximum increase. So that's kind of something important to think about. The gradient vector points in the direction of maximum increase. Okay, so if you were to take a look again at that 3D surface and you were to find the point, let's see, if x is 1 and y is 2, so we'd be at the point 1, 2, 4 on that surface, you would see that the gradient is going to be in the direction of where we're increasing the steepest on that surface. Okay, and the gradient, I'm getting too far ahead of myself. The gradient at 1, 2 is, let's see, it's going to be negative 4. When I plug in 2 for y and 1 for x, and 4, right? Okay, so on this surface at the point 1, 2, right, because f of 1, 2 is 4. Okay, so at the point 1, 2, 4, if I look following this gradient vector, negative x, we could scale it down to negative 1, 1. In that direction is where we'd be like pointing steep up the steepest hill there. Okay, so again, I would strongly encourage you to take a look at that. And then the magnitude would give us how steep it is too. But there you go. So it's going to point in the maximum increase. The rate of change, so now it's asking for the rate of change in this direction, so not in the same direction as the gradient vector, okay? So what that's asking you to do is to take the gradient and dot it with u. Okay, again, and I'll show you the gradient dotted with itself. Okay, we'll give you the maximum increase. But so then we're going to do negative 4, 4, dotted with our unit vector. So we're going to have to do the magnitude of 2 square root of 5 would be the square root of 4 plus 5, which is 3. Okay, so we're going to have 2 over 3 square root of 5 over 3. Okay, so that dot product is negative 8 over 3 plus 4 square root of 5 over 3. So 4 square root of 5 minus 8 over 3. And that is the rate of change in that direction. Okay, if we want the rate of change in the direction of our gradient vector, okay, nope, I don't want to do that. And this is not an example in the book, but it's kind of a logical question to follow. So if we find the rate of change of f at 1, 2 in the direction of the gradient, which is negative 4, 4. Okay, so in this case, we'd have negative 4, 4 dotted with the magnitude would be 16 plus 16 square root, right? Which would be the square root of 32, which would be 4 square root of 2. So we'd have 4 over the square root of 2 plus 4 over the square root of 2, which would be 8 over the square root of 2, which is 8 square root of 2 over 2, which is 4 root 2. Okay, which, right, it's just the magnitude of that vector, the magnitude of the gradient vector. Okay, so it's going in the direction negative 4, 4, and this is kind of the rate at which that's the rate at which it's going in the direction. Okay, so that's going to be the steepest. All right, the last thing I'm going to kind of talk about here a little bit, and they always kind of follow it up, is if we have functions in 3 variables or any more than 2, you just carry on the pattern. Right, so it'd be okay, and everything, the calculations still apply. Your directional derivative is still the gradient. Sometimes you just do the gradient like that. You can put the subscripts just like that. Okay, and we could continue with even more than 3 variables. All right, next thing is maximizing the directional derivative. Maximizing, which we kind of just talked about. I keep getting ahead of myself in these. Okay, suppose f is a differentiable function in 2 or 3 or even more variables. The maximum value of the directional derivative is the magnitude of the gradient. Oops, too many parentheses there. And it occurs when u has the same direction as the gradient vector. What did I say about my handwriting? I'm already losing it. Okay, so that makes sense, right? If your gradient vector is pointing in the direction of maximum increase, then the magnitude of your gradient vector is going to be your maximum increase. Okay, it's going to be how steep it is. Makes sense. All right. So a little example here. Find the maximum rate of change of f of st equals t e to the st. Oh, that's a scary word. At 0, 2, and the direction in which it occurs. Okay, so we already know the direction is going to be whatever the gradient is. And, they're using S's and T's instead of X's and Y's. That's okay. We're going to keep them in alphabetical order and find the partials. So the partial in S would be, let's see, t squared e to the st. And the partial in t, we'd have to do a little bit of a chain rule there. First times the derivative of the second plus the second times the derivative of the first. So we would typically write that something like that. Okay, so that's your gradient. So if I plug in 0, 2, let's see, if S is 0 and T is 2, I'm going to have 4. And if S is 0, 1 times e to the 0, so 1. Okay, so that's the direction. And then the magnitude would be the square root of 4 squared plus 1 squared, so the square root of 17. Okay, so the maximum rate of change is square root of 17, and the direction in which it occurs is in the direction of 4, 1. Okay. All right, so we're going to move on here a little bit. Hopefully those were some pretty good examples for you. I think it's pretty clear, right? All right. We're going to talk about tangent planes to level surfaces. Okay, so a little bit of like some of the background stuff here, where sometimes I kind of lose you guys. It's okay. Follow along as best you can. So we have a surface S, f of x, y, z equals k. So you can think about it as like a level surface, which we talked about in chapter 10. It's almost like shells, like, you think about those Russian nesting dolls, like we have one shell, one K is valley, and then we get another shell. So these are level surfaces are parts of solids, okay? And let's say some point is on that surface, okay? So an example that we're going to use is x squared over 4 plus y squared plus z squared over 9 equals 3. That's an ellipsoid, okay? And the point -2, 1, -3 is on it, okay? And you could just check. You could plug that in and see that it makes it true, right? It would make it 1, 1, 1. 1 plus 1 plus 1 is 3, okay? You could take the time to figure out when x is 0 what it looks like, when y is 0 what it looks like, when z is 0 what it looks like. But basically, draw in the intercepts for you here. So if you want to pause and take some time, it's really good practice to kind of figure out what these things look like. But it would just make the video way too long if I tried right now. So we would have at 3 root 3 and at negative 3 root 3 on the z. And the x, we're going to go to 2 root 3 and negative 2 root 3. And then the y, we got root 3 and negative root 3. Okay, so we can kind of try to picture these ellipses. It's kind of eggish shape, I guess. Okay. And then your point, let's see, negative 2, 1, negative 2, 1, negative 3. So like, okay, it's one of the points on there. All right. So I'm going to add more to this little definition here, but this is the one that we're going to use when you do examples. C is a curve on S that passes through P. Okay, so let's say that we've got, let me label, this is P, the purple guy is S. Here, I'm actually going to do green is P, purple is S. And then we'll do a reddish color for C. Okay, so just as long, C is like some curve that goes around the surface. And it's on the surface and it goes through point P. Okay, so if it's a curve, C would have an equation, a vector equation. Okay, and there has to be some t value where we would get x naught, y naught, z naught, right? Which is point P. Okay. Now we're going to get a little bit to what we did with the last section. Since C is on S, then what has to be true is that your function, okay, back up to the purple guy, right? This f of x of t, y of t, z of t equals k. Okay. I guess we don't have to do since. We're getting there. This is not a result of the since part, okay? But we can differentiate. With respect to t. Okay, so with respect to t. So that's where your chain rule comes in, right? So we do the derivative with respect to x, which would be a partial, and then dx dt with respect to y, which would be a partial, and then dy dt with respect to z, which would be a partial, and then dz dt would have to equal 0. Okay, well, what we have here really is we have the gradient of f dot product with r prime of t. Okay, the gradient of f, right? The partial with respect to x, the partial with respect to y, and the partial with respect to z, and then r prime, which would be dx dt, dy dt, and dz dt. So that has to equal 0 okay? Which means at every point, it would have to equal 0. So our gradient at P dotted with our tangent vector at T, at P, has to equal 0. Okay, so what that means then too is that the gradient of F at x naught, y naught, z naught is perpendicular to our tangent vector. That's huge, okay, because we know that the tangent vector would be in the tangent plane. So then we know the normal vector to our tangent plane, okay? So this is in the tangent plane, which means this is a normal vector. And we also have point P is in the tangent plane. So what all this is getting at is that we can easily come up with the equation of the tangent plane. Okay, we can easily find the gradient at the point. So that's huge, because if you remember in chapter 10, finding the equations of the tangent planes wasn't so easy. I do want to point something out here. A lot of kids get confused about the fact that the gradient is perpendicular to our surface. Okay, it seems like when we were just doing the surfaces, the gradient was pointing in the direction of maximum increase on the surface. Now all of a sudden it's perpendicular. Okay, what we need to think about here is the fact that this is a level surface. So you have to think about these all nested together. I don't know if you guys know what Russian nesting dolls are, but if we had, I'm not even going to try to draw a doll. If these were our level surfaces, maybe it's like a bell shape here. Okay, here. Kind of reminds me of candy corn or something. Okay, the gradient points in the maximum increase in the surfaces. So what's going to get you quickest through the surfaces? Okay, so it's always perpendicular to the surface, because that would be the quickest way to the next surface. So don't confuse what we just did. What we just did, we're not talking about on a single surface. We're talking about level surfaces in a volume. So your gradient points in basically like the quickest way out of that volume, okay? Where those level curves are the closest together, all right? Okay, we're actually almost done with this one, okay? So what we know now then is that since our gradient is the normal vector, let's go back to our equation of a tangent plane. So then the tangent plane would be your partial in respect to x at that point times x minus x naught plus your partial with respect to y at that point times y minus y naught plus partial with respect to z at that point times z minus z naught equals 0. Okay, so you could go back and look at some of the things that we did in chapter 10 and see how much easier it is now that you know gradients. Okay, we also learned that the symmetric equations of the normal line then would be in chapter 10 we used a, b, and c for those coefficients, x minus x naught over the partial y minus y naught over the partial and z minus z naught over the partial. Okay. We can get to a special case here that the book kind of points out when we have our surfaces. where z is a function of x and y instead of a function of x, y, and z, then what happens there is our partial with respect to, let's see, sorry, our capital F would be f of xy minus z. Remember we said it equal to 0? So the partial with respect to x would be just be whatever, you know, that lowercase f partial. Partial with respect to y, and the partial with respect to z would be -1. So we would have the equation of that tangent plane simplifies down just a little bit. Okay. So back to our example, which actually I'm going to just take it right down here with me. Let me grab. Oh, what did I just do? I thought I had my grabbing tool here. Okay, let's get this a little bit better. Maybe. Let's try that again. There we go. That's going to work better. Okay. Oh, I don't need all that. Oh, well, it's okay. Move this guy down. Oh, that's not going to work at all, is it? Nope. Undo that. Undo. Undo. So yeah, always things just fall apart at the end of the video, don't they? We're going to go back up to here. We're going to leave that guy there. Okay, so our example back up here, we're going to find the tangent plane and the normal line. Okay, so find the tangent plane and normal line at -2, 1, -3. Okay. All right. So remember, you want to kind of have it set equal to 0, right? Before you start taking the partials. It's not really going to matter because the derivative of 3 is just going to be 0. But technically, we should get that 3 on the other side. Okay. But we're going to be looking at here. I'll just change it. -3 = 0. Okay. So that's your f of x, y, z. And remember, we called that capital F because everything's on one side, and we're ready to take the partial derivatives. Okay? So your partial with respect to x would just be x over 2, right? That x squared over 4, that's it. Everything else goes to 0. Your partial with respect to y would be 2y. And your partial with respect to z is going to be 2z over 9. Okay? If we take all of these at 2, 1, -3, then your partial with respect to x will be 1. Oh, I'm sorry, it's a -2. -1. Your partial with respect to y will be 2. Your partial with respect to z will be -2/3. Okay, so your tangent plane, we're going to have -1 times x minus -2 plus 2 times y minus 1 plus -2/3 times z plus 3 equals 0. So -x minus 2 plus 2y minus 2 minus 2/3 z minus 2 equals 0. So we're going to have -x plus 2y minus 2/3 z equals 6. Did I just do that right? Yes. Okay. Typically, we would scale that up by a factor of -3. So if the x is positive, we don't have any fractions. So 3x minus 6y plus 2z equals -18. Okay. your normal line then, we would have, so there's your tangent plane, and we're almost done. I'm going to clear out some of this stuff over here so I can write here. Okay, so then your normal line, remember, would be x minus x naught, so x plus 2 over that partial in x, which would be negative 1, equals y minus 1 over 2 equals z plus 3 over negative 2/3. And again, that's something where maybe we would multiply by 3, everything, or actually just the last one, I'm sorry. So we could also write that one is 3z plus 9 over negative 2. Okay? And that's your symmetric equations for that normal line. Okay? That's it for this section. So a little bit shorter and easier than the last one, I think. There you go.